Okay, so picture this, an orchestra, but with billions of musicians. Now try to imagine getting every single one of them to play in perfect time, right down to the pick a second. That's basically the insane challenge happening inside every microchip. The clock signal is the conductor. It's the very heartbeat of our digital world. So how in the world do they pull it off? Let's get into it.
And really, that's the big question here. I mean, think about it. The chip in your phone, your computer, it's got billions of these tiny little switches, these transistors, that all have to flip in perfect, flawless unison. How is that level of synchronization even possible? The most obvious approach, right? Just run one wire from a single clock source to everything. Well, that would be a total disaster. You see, the signal has to travel different distances to get to different parts of the chip. And when you're dealing with nanoseconds, that tiny difference in distance becomes a huge difference in time.
So before the engineers get to work, the whole situation is, frankly, a mess. The clock signal starts out as just one source trying to drive millions, sometimes billions, of destinations all at once. It's what's known as a high fan-out problem. It's got no help, no buffers, and it's just not ready for the most important job on the chip.
Right, so this is where we begin. Just one signal coming from one spot. It sounds simple enough, but this one little fact is the source of a massive physics problem. A problem so big it could make the whole chip completely useless.
And that problem, the big bad villain of our story, is something called clock skew. It's just this unavoidable performance-killing thing that happens because, well, signals don't travel instantly. It takes time for an electrical signal to travel down a wire. So what is it, exactly? Simply put, clock skew is just the difference in when that tick of the clock actually arrives at different parts of the chip. And if we go back to our orchestra analogy, if the violins hear the beat a split second after the drums, the whole performance just descends into noise.
Yeah, and this diagram here? It shows you exactly what's happening. You've got that original clock pulse, but the signal that gets to one part of the chip, let's call it CLK1, arrives at time T1. The signal that gets to another part, CLK2, arrives a tiny bit later, at time T2. That little difference, that gap between when they arrive, that is skew.
And this shows you why it happens in the physical world. The wire going to register 1 has a certain length, D1, and the wire going to register 2 has a different length, D2. The path lengths are different, so the arrival times are different. It's a simple concept, but it's incredibly destructive to a chip's performance.
So the big question is, how do engineers beat this fundamental law of physics? Well, turns out they don't fight it. They get clever. They design around it with this really elegant solution called a clock tree. And the whole process is called clock tree synthesis, or CTS for short. Basically, it's the art of deliberately building out this delivery network, not as some tangled web, but as a perfectly structured network designed to make sure that arrival time difference is as close to zero as humanly possible.
So here's our before picture. The main clock, CLK, is just branching out all over the place. The paths have different lengths. There's nothing there to boost the signal along the way. This is pretty much a textbook recipe for terrible, disastrous clock skew.
Your first thought might be, hey, let's just use a bigger, fatter wire, right? But nope, that's not the solution. The real answer is way more clever. The secret sauce is building a tree made of what are called buffers. You can think of these buffers like little signal boosters, or maybe like relay runners in a race. They grab the signal, clean it up, give it a fresh push, and send it on to the next stop, making sure it arrives strong and on time. And voila, here is the result. This right here is the masterpiece created by CTS. Instead of those long random paths, the signal is now distributed through this beautiful symmetric tree of buffers. Now, the journey from the clock source to every single endpoint is practically identical. It's taking pure chaos and turning it into perfect order. But of course, it's not quite as simple as just making all the paths the same length. It's actually this super sophisticated balancing act, a real puzzle with a bunch of rules and goals that engineers have to juggle. So engineers are really dealing with two different kinds of goals here. You've got constraints on one side. Think of these as the hard rules, the laws of physics. You break these, the chip just won't work, period. And then on the other side, you have targets. Things like minimizing that skew we talked about. These are the goals you're aiming for to make the chip as fast and efficient as possible.
And believe it or not, it gets even more detailed than that. See, engineers can choose different strategies. They might focus on global skew, which is balancing the clock across the entire chip. Or they might zoom in on local skew, which is just about making sure a few components that work together are perfectly in sync. And this choice leads to some really interesting trade-offs. Okay, check this out. This is a perfect example of what I mean. So on the left, using one approach, the clock hits component A at 0.3 nanoseconds and B at 0.38. Close, but not perfect. But look at the right. By focusing on just these two with a local skew strategy, the engineers nail it. The signal arrives at both A and B at the exact same time, 0.2 nanoseconds. Now, getting that kind of local precision can really boost performance, but it usually means the design process gets a lot more complicated.
So at the end of the day, after all this work, what's the big picture? What have we actually accomplished? Well, we've taken what seems like an impossible physics problem and completely tamed it, all through some seriously brilliant engineering. And honestly, this slide says it all. This is the big takeaway. You see the chaos on the left, where signals would just be arriving all over the place. And then you see the order on the right, that final, elegant clock tree. It's a synchronized network that provides the stable, reliable heartbeat that the entire chip depends on to function.
Really, it all boils down to one simple but really powerful idea. You build that buffer tree to perfectly balance the electrical load. That way, every path feels identical to the signal. And when you balance the load, you minimize the skew. It's that direct. You know, this whole process is one of those hidden marvels of engineering that just makes our entire digital world possible. But the story isn't over. As we start building chips upwards, stacking them in 3D, this challenge of keeping that perfect heartbeat in sync, it's about to get a whole lot harder. So the real question for the next wave of engineers is, how are they going to conduct an orchestra that's even bigger and way more complex?